Hello, everybody. Welcome back. We are finally going to zero in on this topic of global climate change, something we've been alluding to, talking about, mentioning all year long as a sort of an overarching theme. In Unit 6, we talked really quite often about the importance of finding energy sources that help to reduce or minimize or entirely get rid of our carbon emissions. Here is where we're finally going to talk about why. Why is this such a stinking important topic? Why does Mr. Hudeberg get on his soapbox and tell you that this is the question of the century? Here's why. So don't forget to do your reading, please. It's a long section. My recommendation there is to really take a look at the data sets that book provides, photos and stuff like that. All the text, of course, is good ways to follow up. Uses a different part of your brain when you read versus hear versus talk. But probably the most important things to look at are the data sets in there. So please do yourself a favor and take a look at those pages from the Miller textbook. Now, a real quick terminology check. When we say global warming or climate change, are we talking about the same thing? And short answer is both yes and no. The term global warming is a little bit incomplete and sometimes misleading. Now, is the climate system warming? Yes, it is. We've talked about that in class. You guys have seen that data set. Now, what's important to understand is when we say that it's warming, we notice that, we're talking about 2 degrees Celsius. That seems to our own general experience to sort of minimize what's actually happening, and it's incomplete. So, for example, if it's 95 degrees in July one day, the next day the high is 97. You and I aren't probably really going to notice that difference. That's 2 degrees Celsius difference, which according to climate scientists, if we have a global change of 2 degrees Celsius, we're talking about drastic, huge impacts. Well, if we walk outside and if we feel a 2 degrees Celsius difference, we're like, so what? That's sort of what makes the term global warming incomplete. It's because if we have a global shift of 2 degrees Celsius, we're talking not just about the fact that areas will be warmer, the ocean will be warmer, the surface, the atmosphere is warmer. We're talking about different amounts of moisture in the air. We're talking about changing our ocean currents. We're talking about changing our ice caps, rising sea levels. We're talking about less snowpack in the mountains, more severe summer droughts, crazier storms because there's more energy in the atmosphere. So many things that are drastic by our standards don't emerge when we just say the term global warming. So that is why climate scientists think it's more accurate to describe it as climate change. Now, other thing is we have this central premise, and this is really what people who don't know what they're talking about try to argue, is that the Earth changes climate on its own, that the Earth's history is full of climate change, and they're 100% correct. That is very, very well documented. Ice ages and interglacial periods. We go back to the dinosaurs, and it was crazy, crazy hot. No ice anywhere on the planet. We go back even farther, and we have the entire Earth was almost one big block of ice. There's these crazy climate changes that have happened in the past. The central premise of what we're talking about now is that, yes, climate does change due to factors outside of our control, but the warming that we're seeing now is at least mostly anthropogenic. We will learn in class kind of why climate scientists have come to that conclusion, that it is in fact caused by humans this time, as opposed to something naturally occurring that we're just going to have to adapt to. Okay? And let's remember that vocab term is that anthropogenic means originating from human activity. So this is our central premise. It is anthropogenic. We will chat in class about how climate scientists know that. We're going to focus on, okay, so climate's changing, kind of so what? What does that mean for us? But let's begin with that premise. Okay, let's dig in. So what if it's getting a little warmer? We have to first of all understand that modern society, where our cities are, where our farms are, how we get our water. All of these systems, all of this infrastructure is built on climate as it is and has been for decades leading up to it. So economies and cities are built based on a certain availability of water in that regional location. If precipitation patterns change, if precipitation type changes, that's going to change when water is available, how much water is available in different regions of the world in different ways. Farmers plant crops. Which crops they plant, when they plant those crops. That's based on some of climate factors. Things are going to have to change if we have a warming surface. Sea levels are steadily rising. That's going to displace millions of people all over the planet. A huge percentage of the population lives within just a few meters of sea level. Specialist species, we've already chatted about this. These specialist species that already have a super high extinction rate, those rates are just likely to increase as climate changes. So this sort of goes on. I'm not trying to spell doom and gloom. We're just trying to understand the magnitude of this very real problem. So let's dig in. Let's chat about model projections. So we have direct observations, things that we can directly measure. We go farther back in time. In class, we've talked about what proxy measurements are. Okay. Well, how do we look forward? So if we're going beyond what we can directly measure and trying to make predictions. So if we understand the climate system well, if we have sufficient computing power, we can make at least somewhat accurate predictions about what things might look like in the future. Now, so the IPCC, the Intergovernmental Panel on Climate Change, takes all the best science we have available to us, and they work together to try to help us understand what things might look like in the future. So in this example right here, what you're looking at is projected global surface warming based on different scenarios. So for example, if we were just to stop pumping CO2, like we hit a big switch, we've moved all the way over to clean renewable energy. That's just what would have happened. We would have sort of increased very slightly as the Earth reestablishes equilibrium at or near that current level of warming. Okay, now, well, we didn't have that capability. We still don't have that capability. We can't just turn a giant switch. Okay, so we're going to have some sort of transition period. What they show here are different levels of aggression for that transition. So if we go low growth, this scenario, this is where the global community just decides to aggressively attack this problem. So in that case, we might keep ourselves at or below about a 1.5 degree Celsius warming with a relatively large degree of uncertainty. Moderate growth, which means we do still, as a global community, decide to limit or reduce emissions, but at a more reasonable pace, reasonable in the sense of something that's probably not going to take super drastic efforts. That's that green level of uncertainty. And then if we just kind of decide to keep running amok and not really drastically change our behaviors, that's that red scenario. So we could end up anywhere from less than 1.5 degrees Celsius all the way up to something like 4 degrees Celsius. That's a huge range of potential impacts. So, rising sea levels. We have the red line, which is tide gauges. We have the blue line, which is where they started to switch over to satellite technology to make those measurements. We have the IPCC projections. Again, projections are what they predicted for sea level rise in the future. You guys can see that as of the time this graph was put out, we had about a 6 centimeter global sea level rise. 6 centimeters, 6/100ths of a meter. Again, doesn't seem super drastic. Notice too that our direct measurements are running us at the high end of what the IPCC projected from 1990 onward. We can look forward into the future. So again, we were, first of all, let's establish our zero line. These are not in the same place. The zero line on this graph is sea level in 1700. The zero line here is sea level in 1990. So our zero line needs to be adjusted here. But here we are today. So it looks like about 6 centimeters on this graph. It was closer to about 20 or 30 centimeters on this graph. Let's clarify that. Now, what are we looking at in the future? Again, low growth scenario puts us between 0.5 meter to 3/4 of a meter. High growth scenario puts us between 3/4 of a meter to more than 1 meter. And again, what does that seem like in context? Well, if you live in Seattle or New York or Los Angeles or San Francisco or other coastal cities all over the world, that means you are moving inland away from that city. 2 causes of sea level rise. Let's understand why we have sea level rise in the first place. So there's 2 causes. 1, thermal expansion. As you heat a liquid up, those molecules of that liquid tend to move a little more quickly and occupy a little more space. That's thermal expansion. You guys should have learned about that in middle school. If we warm the ocean up, ocean's going to expand, volume will increase. We will see sea level rise increase as the oceans warm. We also have to understand that in some cases we are adding additional water to the ocean itself. So we're not talking about that Arctic sea ice. If the icebergs, okay, those are not going to directly cause sea level rise. That's water that's already in the ocean itself. Okay, we're talking about the melting of our big ice caps. So Greenland is a landmass with a ton of ice on it. Antarctica, also a landmass with a ton of ice on it. If we melt the land ice, those ice sheets, okay, that's taking, so this is our ocean, this is our land, that's taking water that's on land and returning it to the ocean. Ocean levels rise accordingly. Okay, so let's make sure we understand those are the 2 causes of sea level rise. So impacts of sea level rise. There's lots that could be going on here. We are just by, like, for example, a 1 meter sea level rise going to impact where our photic and aphotic zones are. So photic, remember, is the depth to which light penetrates. Our neritic zone and intertidal zones are going to adjust. We're going to reduce certain habitats that are near sea level. 1 meter of sea level rise can sort of adjust these systems and sometimes adjust them too quickly. Coral, for example, is very sensitive to the amount of light penetration. Where that photic zone is has very big impacts on where we find coral. Remember, coral is one of our most important ecosystems. Much of ocean life lives at least some part of its life is tied to coral reefs. If sea levels rise faster than coral is able to grow, that can have big impacts on our coral reef systems. All right. So what regions of the world are going to be most affected? Again, we're looking at what percentage, how much of the population lives near or within a couple meters of sea level. So we can kind of see from this graphic right here that China and India, 2 developing countries, they're really trying to turn a corner and develop economically and raise the standard of living there. Those are the type of countries that are going to be most impacted. Obviously, we already mentioned some important U.S. cities, etc. Okay, let's look at the Arctic. Go up to the northern reaches of the globe. Polar regions show an accelerated response. So when we're experiencing 1 to 2 degrees, they might see double or even more of that overall change in average temperatures in the polar region. So part of that is they're having more pronounced changes due to surface albedo. So remember, we talked about that in a previous unit. If there's ice on the ground, that reflects more sunlight. That would tend to help keep that general area a little cooler. More sunlight's reflected, less is absorbed in that case. As those polar regions warm, the amount of ice retreats, and we see a decrease in albedo. More absorption contributes to more warming. Thawing permafrost emits methane. We already mentioned that methane is 20 plus times more potent of a greenhouse gas than carbon dioxide is. That creates these positive feedbacks. You should remember all the way back to Unit 1 when I first introduced those terms. Right? So positive feedback is something that reinforces. So it takes the initial change and makes it bigger. So we have two feedbacks that are important in the Arctic. One is that albedo feedback. Sea ice loss increases the absorption of sunlight. So the albedo change, which makes it even warmer, which melts more sea ice, changes the albedo more, makes it even warmer. Arctic methane. So the permafrost is beginning to thaw. We have anaerobic decomposition that releases methane into the atmosphere. Okay? When that methane is released, that absorbs more solar energy, which accelerates the warming, which thaws more permafrost, releases more methane, causes more warming. Two super important feedbacks. That is a big cause of why the Arctic is warming faster than other regions. Now, we have some specialist species living in the Arctic. Polar bears, Arctic foxes, etc., who are heavily reliant on the existence of that ice. They have adapted over very, very long periods of time. Their food chain is heavily reliant on ice cycles. As that ice retreats, so does the habitat and opportunities for those specialist species in the Arctic. In the atmosphere, right, we could likely see a change in our prevailing winds. Those patterns are going to shift. That's going to cause changes in patterns in our precipitation. Dry areas are likely to become drier. Wet areas are likely to experience in more intense storms and actually increased rainfall. The precipitation type may change. And again, this really hits home here. We might see more rainfall in Walla Walla, but we're also likely to see less snowfall, which impacts our ability to get water during our dry months because we rely on the fact that snow falls in the winter, gets stored up in the mountains, melts slowly throughout the spring and summer, keeps water flowing in our streams. Now, we're putting more energy in the atmosphere. That creates more opportunities for intense storms. So believe it or not, we might see an increased frequency of blizzards as these snowstorms that come through might have a little bit more punch to them because of the increased energy. We're likely to see increased probability for the conditions that lead to hurricanes. We're already seeing more frequent floods, heat waves. As things get drier here in the West, right, we're likely to see increased wildfires and things like that. Climate scientists have a high degree of certainty for general changes, but low certainty on the regional scale. So, for example, they're pretty sure all these things are going to become more likely. More heat waves, more floods, more hurricanes. In fact, oddly enough, more blizzards. Where and exactly how the Pacific Northwest might be impacted, we can understand the snowpack thing. It's really difficult to understand and predict how much our overall precipitation might change. So climate scientists have gotten pretty good at generalizing predictions, not super good yet at fine-tuning those predictions on kind of a smaller time scale or the regional scale. Let's talk agriculture. So general decrease in snowpack is going to affect our ability to irrigate in the summer months. Increased evaporation. When the atmosphere is warmer, we're going to evaporate water faster from the soil, which is just going to increase how much water we need in the first place. In some cases where we talked about increased precipitation, that's going to cause more soil erosion, more leaching of nutrients. Interestingly, some of our higher latitudes, places like Canada and Russia, they might actually see an improved soil quality because their climates in a warming system will moderate somewhat. So we actually have a differentiation in whether it's sort of a helpful thing for a region, perhaps, or an exceptionally harmful. Now, if we look at it as a whole, right, the negative sides far outweigh the positive sides, but it is worth pointing out that some regions might see more temperate conditions and improved soil quality. So looking at the United States, for example, right, we can see, well, not just the United States, but over the whole, but we can look at portions of the United States, the Rockies and Plains, Pacific Northwest. Some models predict that we will actually see a nice increase in agricultural production in the Northwest and the Rockies. That'll be accompanied by a significant decrease in both the southeastern United States and Southwest Plains. But look at places like India, one of our fastest growing countries, Mexico, Australia, China, moderate increase, Canada, moderate increase. Okay, so by the 2080s, again, different regions are going to experience the impacts of climate change in different ways. All right, that takes us to the end. Adios.